Hey there, welders, metalheads, and anyone who's ever stared at a glowing bead of molten steel and thought, man, there's gotta be some wizardry behind all this. Welcome to the first episode of Forge and Flame, Metallurgy for Welders, where we break down the science of metal in a way that won't put you to sleep or make you feel like you're back in high school chemistry. Now, before we jump in, let me set the stage. Picture Conan the Barbarian. You know the guy. Shirtless, swinging a massive broadsword, muscles glistening, looking like he just emerged from a medieval sauna. You might not know this, but Conan's iconic sword wasn't forged in one go. Nope, it was heat-treated, tempered, and quenched to perfection, just like every tool, part, or weld that holds up under pressure. That's heat treatment in action. Today, we're diving into the basics of heat treatment, what it is, why it matters, and how it ties into the welding work you do every day. No fluff, no overcomplicated science. Just straight up practical knowledge to help you be a better welder and understand the steel you work with. Section 1. What the heck is heat treatment? All right, let's start simple. Heat treatment is like giving steel a personality adjustment. You're changing its properties, hardness, toughness, all those fancy words, by heating it up to specific temperatures, holding it there, and then cooling it back down. Think of it like cooking, but instead of a steak, you're working with steel that's got to perform under stress. Here's the thing though, steel isn't just one size fits all. It's made up of iron with a bit of carbon sprinkled in, and sometimes other elements like chromium, manganese, or molybdenum, depending on the type. The way you heat and cool that mix determines if you get something tough like armor or brittle like glass. Ever had a weld crack on you? That's probably because the heat treatment, or lack thereof, didn't line up with what the steel needed. Knowing how to heat treat can make the difference between a weld that holds and one that fails when the pressure's on. Section 2. The big players in heat treatment. Heat treatment comes down to a few key processes. Let's hit the highlights. 1. Annealing. Think of annealing like giving steel a spa day. You heat it up, let it soak at a high temperature, and then cool it slowly, like a nice, relaxing cool down. This makes the steel softer and easier to machine or shape. Perfect if you've got a part that's been through the ringer and needs a little TLC. Number 2. Quenching. Here's where things get dramatic. Quenching is like the Conan sword moment. You heat the steel up and then dunk it in something like oil, water, or even air to cool it fast. This locks in hardness but can make the steel brittle, like glass. That's why you'll usually follow it up with 3. Tempering. Tempering is the fixed attitude problem. You reheat the steel to a lower temperature to trade some of that hardness for toughness. The result? A part that can take a beating without cracking. 4. Normalizing. This one's all about balance. You heat the steel to a temperature above its critical point and then let it air cool. It's like resetting the steel's microstructure to get a good balance of strength and ductility. Think of it as a middle ground between annealing and quenching. Section 3. Why welders should care. Now you might be thinking, okay, but I'm just here to burn rods and make sparks fly. Why should I care about heat treatment? Well, here's the deal. Every time you strike an arc, you're heat treating. That heat from the welding process doesn't just join metal. It changes the properties of the material around the weld, known as the heat-affected zone, or AISI. Ever had a weld look perfect, but it cracks a week later when the part's in service? That's because AISI can end up harder, more brittle, or more stressed than the base metal. Understanding how heat treatment works helps you avoid those headaches and turn out welds that last. All right, let's zero in on one of the most important and sometimes infuriating parts of welding, the heat-affected zone, or HAZ. This is the area of the base metal right next to your weld that gets cooked by the heat of your arc. It doesn't melt, but it gets hot enough to change the structure of the steel. Think of it like the edge of a steak, seared on the outside, but not quite cooked through. Now here's the kicker. The HAZ is where things can go sideways. Too much heat and the steel gets brittle. Not enough, and you might not get proper fusion. The trick is controlling that heat to get just the right balance. Section 5. What happens in the AZ? To really understand the HAZ, you gotta know a bit about steel's microstructure. When steel heats up and cools down, its internal structure changes, These changes are all about the phases of steel, and there are three main ones to keep in mind. 1. Ferrite and perlite. This is your baseline structure, strong, ductile, and easy to work with. This is where you want most of your base metal to stay. 2. Austenite. When you heat steel past its critical temperature, it transforms into a phase called austenite. This phase is like molten wax. It's malleable and ready to take on new forms. 3. Martensite. Now, if you cool that austenite too fast, say by quenching, it turns into martensite. Martensite is hard, which sounds great, but it's also brittle. Imagine a toughened glass windshield. It can take some hits, but when it goes, it shatters. That's martensite in action. In the AISI, you're playing with all three of these structures. If the steel cools too fast, you might end up with brittle martensite right next to your weld. That's a recipe for cracking, especially if the part's under stress. Section 6, Preheating and Why It Matters. Now let's talk solutions. One of the best ways to manage the AISI and avoid nasty surprises is preheating. Preheating is exactly what it sounds like. You heat the base metal before you weld. Here's why it works. Slows the cooling rate. When the metal cools more slowly, you reduce the chance of forming brittle martensite. Reduces thermal stress. Welding creates crazy temperature differences between the weld and the surrounding metal. Preheating evens things so you're less likely to see cracks. Improves fusion. A warmer base metal helps your weld penetrate better, leading to stronger joints. So how hot are we talking? That depends on the material. Carbon steels might need preheat temps around 250 to 400 degrees East Celsius, while high-strength alloys can go higher. Just don't wing it. Check your welding procedure specs or consult an engineer if you're unsure. Section 7. Post-weld heat treatment. Okay, you've made your weld, the ASME looks decent, and you're ready to call it a day. Not so fast. Depending on the job, you might need to follow up with post-weld heat treatment, or PWHT. PWHT is like therapy for your weld. It relieves residual stresses, softens the ASME, and improves toughness. Think of it as giving your weld time to relax and settle into its final form. There are a couple of ways to do this. 1. Stress relief. You heat the part to a specific temperature, below the critical range, and hold it there for a while before cooling. This process reduces internal stresses without messing up the steel's structure. 2. Temper bead welding. In some cases, you can temper the ASME right in the welding process by layering beads in a specific way. This is an advanced move, but it's worth knowing about. The key takeaway? PWHT isn't just extra work. It's insurance. It makes sure your welds can handle the pressure, whether that's in a high-pressure pipe or a crane lifting a massive load. Common mistakes to avoid. Let's wrap up with a few common mistakes welders make when it comes to heat treatment. 1. Skip and preheat. Look, I get it. Preheating takes time, and sometimes you just want to strike an arc and get it done. But skipping preheat is like skipping leg day at the gym. Sure, you can get away with it sometimes, but eventually it'll catch up to you. 2. Rushing the cooling process. Don't dunk that part in water unless you know it needs a fast quench. Slow, controlled cooling is your friend in most cases. 3. Not following procedures. Every material and weld type has its own sweet spot for heat treatment. Skipping the procedure specs or winging it is a gamble, and the odds aren't in your favor. Part 3. Understanding weldability and cracking. All right, now that we've laid the groundwork in Part 1 and Part 2, let's dive into a key aspect of welding. Weldability. If you've ever struggled with cracks or weld defects, this part's for you. And no, we're not talking about the kind of crack that's in your coffee cup, but rather the cracks that happen in your welds. The term weldability is important. As the AWS, American Welding Society, puts it, weldability is the capacity of a metal to be welded under specific conditions and still perform well under the stresses of its intended. When you're welding a job, especially on things like buildings, bridges, or pipelines, you're dealing with materials that have been carefully selected for their chemical composition and mechanical properties. Now let's bring it back to some real-world context. Common steel materials like ASTM A36 and A5440 are typically used in welded construction, but each one has different behaviors when it comes to welding, especially when it comes to things like cracking. These materials can be more or less susceptible to defects depending on their alloy content, how much carbon is in them, and the overall weld procedure used. Cracking. The unwanted guest. Let's face it, cracking in a weld is about as welcome as a cat at a dog party. Cracks can happen for a number of reasons, but the most common culprits are either hot tearing, high temp cracks, or cold cracking, low temp cracks. Understanding the difference can help you troubleshoot like a pro. Hot tearing. This happens during the solidification phase when the metal is cooling. Some elements, like sulfur, can cause intergranular tears, which means cracks along the grain boundaries. Imagine the metal being like a bunch of little Legos. If the blocks don't align properly, you get cracks. High sulfur steel is a prime candidate for this. The good news is, manganese is like the bouncer at the club who keeps the troublemakers like sulfur at bay. So, keeping your manganese levels in check can really help prevent these issues. Cold cracking. This one's trickier. Cold happens when the weld cools too quickly and the steel is under a lot of tensile stress. This is often caused by the presence of hydrogen in the weld, which sneaks in from the electrode flux, moisture in the air, or even surface contamination. When the weld metal cools and solidifies, it can get brittle and crack. This is where controlling your preheat temperatures and maintaining interpass temperatures becomes critical. The goal is to slow down that cooling process so you don't create a brittle, hardened structure that's prone to cracking. What's your carbon equivalent, CE? A big player in cold crack is the carbon equivalent, CE. This is a formula that takes into account the carbon and other alloying elements in steel that influence its ability to form martensite, a brittle phase that can crack. The higher the CEs, the more likely cold cracking will happen, especially in thicker plates. If you're welding a high CE steel, preheating the joint and controlling the heat input during welding can help avoid cracking. But here's a fun nugget of info. When you get a material with high-strength, low-alloy, HSLA steels, like those ASTM A514 or A57, be extra cautious. These steels can harden quickly when cooled too fast, and without proper heat control, they'll turn into that brittle, cracking mess we're trying to avoid. Hydrogen and cold cracking, the dynamic duo. Now let's talk about the hydrogen that causes the cold cracking. It's like a sneaky little troublemaker that when trapped in your makes it a lot more likely to crack later on. Hydrogen comes from all over, moisture in the electrode, flux, or even from just the air around the joint. Here's the kicker. Hydrogen-induced cracking doesn't happen instantly. It waits for the right moment. When the weld metal is cooling, when there's tensile stress on it, and when the steel is in a brittle state. That's when it causes the big problems. To prevent this, keep your joint clean, avoid surface contamination, and be mindful of low hydrogen electrodes. After welding, post-weld heat treatment is often recommended. This involves heating the weld to a specific temperature, usually around 300 to 400 degrees Fahrenheit, to give the hydrogen a chance to diffuse out before it causes cracks. Nash stress relief and post-weld heat treatment. Sometimes after you weld, the metal is still under internal stress. These stresses can make your weld more prone to cracking later on, especially when you've got a high-strength steel. This is where post-weld heat treatment, PWHT, comes in. PWHT involves heating the welded structure to a certain temperature and then slowly cooling it to relieve these internal stresses. But be careful. Reheat cracking can happen in steels with high amounts of vanadium or molybdenum, which form carbides that can cause grain boundary cracking if not treated properly. So like a swordsmith tempering steel in the fires, you need to control your heat treatment with care. In conclusion, weld smart, weld safe. To wrap it up, your job as a welder is not just about joining metal together. It's about understanding how the material behaves under different conditions. Keeping track of things like weldability, carbon equivalence, and proper heat treatment practices is crucial for producing high-quality, crack-free welds. By now, you should have a better grasp of why proper welding procedures, like preheating, controlling interpass temperatures, and selecting the right electrodes, are so essential for preventing issues like cracking. Just remember, welding is a science, but it's also an art. Knowing the materials, the process, and the heat treatment can make all the difference and with that, stay sharp out there. No cracks, no defects, just solid welds. Until next time,